Okay, moving on with our transformations. Now we're moving into another very common one, which is known as the principal component analysis. So the the whole point of principal component analysis is reduce dependencies on like within the bands themselves. So I mentioned in the previous video that the bands tend to have some sort of like relationship. If I increase my reflection in green, I might see an increase in blue, I might see an increase in red, and I might see increases in all three just because I have a more of a green reflection. So there's a lot of dependencies, and it's just really the nature of waves, right? So what the principal component analysis aims to do is get rid of that dependency so that we can actually compare sensors. So coming into this, it is really our most powerful tool in change detection and in extracting features. So I'm always looking for what has changed overall for change detection, right? So whether it be looking at individual pixels and looking for change detection or an overall value, I can't do that with individual bands. I can't even really do that with like looking at, near infrared and near infrared. I can't do that with two different sensors. The reason being is because it's just such a there's so much dependency based on the sensor and the time of day and everything else that I can't really extract a true change. So if I use PCA, then now I've got the ability to say, hey, you know what? I can see patterns and I'm pulling out those patterns. So to bring back nightmares for you guys, the the principal component analysis uses the variance and covariance matrix, and it shows the interrelationships between the bands. So you would take your entire image and you would apply your wonderful linear algebra skills that you guys have, and you would get a variance covariance matrix with all your bands. This gets to be a very big matrix because it's based on every single band. So for example, with Landsat 8, we have 11 bands, and with Landsat 7, we have we have 8 bands. So if we use the 11 bands in Landsat 8, even if we use 12, because let's say we use the BQA, if we use 12 bands in the PCA, then we have a 12 by 12 matrix. So that gets pretty big, right? So but the other thing too is that with this matrix, we're going to be looking at, if we're looking specifically at variance and correlation, we'll see that bands 2 and 4, or 3 and 4, have values like 70.9, correlations of 70.9. Sometimes they're even higher. Sometimes they're like 90 something, like 94.8 or 98.7 or something along, again, like a very high correlation. So these values can be so high that really they're showing us the exact same thing. So we're not seeing anything different. So what's the point of having two different bands that show the exact same thing? It just takes up computer memory. So for example, a high correlation means the channels are closely related. So if, like for example, if we have a positive correlation, two bands will go up. If we have a negative, for example, here band 2 and band 4, if it's a negative correlation, if band 2 goes up, band 4 goes down. And so it just gives us that negative value. So we could be really looking at it could be a high negative correlation, or it can be a high positive correlation. If it's 0, it means it has no correlation, but I haven't seen yet a covariance matrix or a correlation matrix with a 0 in it, because everything is correlated. So when we have this duplication of information, we need to pull it out. So we have actually, believe it or not, as complicated as variance and covariance matrices can become, and correlation matrices can become, we can have a linear equation. Everything is based on a linear equation. So we have our coefficients, and then we have our pixel values. And A would be the first first band of the PCA. So we have something called eigenvectors and eigenvalues. I don't know if Sam goes over that with you guys. You're not having to do the math in my class. So we're not going to go too hardcore into it because the computer does everything for you. And if he did do eigenvalues and eigenvectors, it's all related to the covariance matrix. So awesome. Like if you went over it and then you know what I'm talking about. If you have not gone over it, and don't stress too much because you're not doing this by hand, you just have to know and identify, oh, that's an eigenvalue, and oh, that's an eigenvector. So those are the terms you just have to be able to identify. You don't have to calculate. So I'm going to ease some stress about that right now. So the Pca results, there's actually 6 bands that I suggest going with. You can set it to be like 13 bands. You can set it to be 100 depending on how many bands you have. But the idea is that we're trying to get rid of the relationships. And we're trying to reduce the amount of computer memory that we're using to be able to process this. So if we look at Landsat 8, we have 12 bands, including the BQA. Here we have our Pca results, and if I say 6, what does that do for me? So this doesn't change based on adding more bands. Really, it just kind of adds on, and I'll talk about that in a second. But so PC1, which is the first result, which is your first band, and it's going to be labeled PC1, that is the maximum trend. So this is the overall pattern. All of my values throughout the entire image, so this does everything all at once, all of my values for the entire image have a trend that's high in this area and low in this area. And that's what it says. So it might be saying, hey, you know, the trend in the classroom is everybody's wearing jeans. And there's going to be some areas that have dark jeans and some areas that have light jeans. And then we have the PC2, which is the variance. So what that does is it looks at the trend and says how much, it goes down to standard deviation really, with the variance of that graph. But how spread out is this? So, you know, if everyone's in the classroom and not like the trend of the classroom is everyone's wearing jeans, and some areas are darker and some areas are lighter, then what is the actual variance of those values? So if I have white jeans on and the next person has black jeans on, that variance might be quite high. And maybe there's a couple people wearing white jeans and a couple people wearing black jeans. And then some people have dark jeans, some people have light jeans, and then it kind of like blends into like a moderate color. If that's the variance of them, or maybe someone who's wearing like red jeans, you know, like you could have any color anymore. What does that variance look like? So that's what this is measuring, and it gives you a value of that. And then PC3 gives a trend of residuals. And so this is what are the things that don't match that? What does not go with the trend? So for example, if I was wearing a skirt, and it's not jean material, then, or I'm wearing dress pants, or I'm wearing khakis, or I'm wearing anything that's not a jean, that's going to be my residual. So that's the measure of that. So it's measuring that. So in terms of remote sensing, I'm looking at areas that have a high correlation and areas that have low correlation. I'm looking at how much that varies within that pattern. And then what are the things that don't match at all? And they kind of like really kind of go extreme compared to, or different compared to what I would be seeing in that image. It's still, you're still going to see the land because it's still spatially related, but, and you're still going to make out shapes, but you might see different shapes than what you saw before. Then we have PC4, which is the atmospheric scattering and topographic shadowing. So this particular band is kind of neat. If you have humidity that comes through, like, or a strong wind that comes through, you can actually see it in the image. So you'll see like wispy ground and such. It's really kind of cool because you can't see that otherwise. In no other image would you be able to pull that out unless it's the PC4 that you're looking at. And also looks at the topographic shadowing and says, hey, look, there's some shadowing here. PC5 is system noise, so this is all the electronics. There's always noise with electronics, and that's just the nature of things. And especially because it's like being transmitted by noise as well from the satellite to a master control station. So there's other systematic errors that it's pulling out. And then PC6 is like low proportions of variance. So like, you know, what are low contributions to the actual variance itself, and what are low like random noise pixels, and are they high values of noise or low values of noise with respect to the correlation. If you have 6 more because you forgot to change it, all you're doing is adding more noise bands. So we're just kind of separating it out more and more and more. So, but the first 3 are really the most important. The last 3 are kind of my noise that's happening. And you can always create a composite with this. This is actually like one of the coolest composites that you're going to be seeing in total. So again, here, if we go to talk about eigenvalues and eigenvectors and where they come into play, you need to give me the eigenvalues and eigenvectors. The PCA is all based entirely around these values. So if I want to repeat them, I need to have them. So to do this, we look at proportions of variance, and it's all related to the percent variance. So it's also called these too. So you're going to see eigenvalues, and it's going to be for each band. It's going to say what proportion of this band is contributing to the variance. And you also see percent variance as well. So your eigenvalues, if I ask for eigenvalues, all you're looking for is going to be a vector of values, one single vector that has a how much, like the proportion of, or they're actually quite large numbers because we're using physical values, but it's the proportion towards that variance value. And so if I ask for that in the assignment, which I will be, you're going to write out what was the eigenvalues for the 12 bands, because each of those bands contributed to this PCA, and so that tells me how much they did. Then we have our eigenvectors. And the eigenvectors, again, in the software, it does all the math for you, right? It is a big matrix. So it's got like all 12 bands from that Landsat 8. And it's going to give you the coefficients for the PCA equations, right? So we talked about that with the linear equation. So you're going to provide these. You have to provide these with the image. I often suggest to people just take kind of a print screen and just put it into like an appendix, but you should always have these. So that is the PCA. I will be showing, when I go through the lab stuff, I will be showing examples of this, but it's the theory of it. And I will stop this here, and then we'll get into the tassel cap analysis next.